20 seconds now.
明白。
As you can see, the countdown on the screen.
10
10, 9, 8,
7
7, 6, 5, 4, 3, 2, 1.
点火。
Ignition.
起飞。 起飞
Liftoff.
时间：纵4时3度分2幺秒，发动6毫秒。程序转弯。阵地1212跟踪正常。
Personnel on the ground reporting that the remote sensing data indicate that the flight is going smoothly. Why do we need those data?
This is to keep the tracking of the predetermined orbits and the speed and altitude. So to keep track on the normality of this rocket.
And we should also notice that the rocket is not flying straight up. It's going sideways. There's a little turn.
It's called pitch over.
Pitch over.
Yes. So the first critical step will be after the tower is cleared will be the pitch over to the so we call the launch direction. With this direction, we can determine the orbital plane. And from you see, this is a video from the camera mounted on the rocket itself on the core stage. We can see 2 of the 4 boosters. Well, the 4 boosters provided 90% of the thrust during the liftoff. So on this stage, mainly the thrust is from the 4 boosters. And after pitch over, the next critical step will be the separation of these 4 boosters.
Yes.
Yes, exactly.
And we keep hearing that the monitoring and command center reporting how the flight is going to continue. They're going to continue to track the flight of this rocket, and then a few minutes into its flight, we'll see the boosters come off the rocket, and you're looking at the pictures being captured by a camera just attached to the body of that rocket, showing, as Professor Yang mentioned, 2 of the boosters there. There are a total of 4 boosters on the body of the rocket. They will all come off later in the flight and allow the separation of the first and second stage rockets.
So each of the booster has 2 engines. So total of 8 engines on the booster, and also engines on the core stage. So the boosters are composed by liquid kerosene, liquid oxygen rocket engine. But the core is cryogenic, which is liquid oxygen and liquid hydrogen.
Help us understand the choice of fuel here.
Well, the liquid kerosene, liquid oxygen works very well in the atmosphere, where the liquid oxygen and liquid hydrogen works better in outer space, which has better propellant propulsion rates.
Okay, the boosters
and
have
the
been
boosters
separated very
are
properly.
being separated. They come off to, because they burn out the fuel, they have to come up to allow the rocket to continue flying.
So now we see the core engine is burning, which is the liquid oxygen and liquid hydrogen.
So at this stage of the flight, what the rocket is doing is that it's accelerating in terms of speed, and until it reaches that height, it will continue to increase velocity.
Yes, it was increasing the velocity and altitude at the same time.
From this 3D animation, we can see the data link from the vehicle to different ground stations. We have ground stations at the launch center, and also have the stations in the Xisha Islands, and also at every critical point. For instance, before the spacecraft separation from the rocket, we also have the ground space tracking ships in the Pacific Ocean.
The number we see on the screen is the number of seconds into the flight. So we're now more than 4 minutes into the flight.
At the current stage, the core stage work with the what's so-called the YF-77 rocket engines. We use 2 engines in this core stage of the Long March 5. Each have a thrust about 50 tons. So this rocket engine is the largest, as Mr. Xu has mentioned, the liquid hydrogen and the liquid oxygen engine, which has the highest specific impulse in China's rocket engine families.
And the next noticeable development would be the separation of the first stage and second stage rockets. How long till we have that? A couple minutes?
零水3901跟踪正常。
This is a camera video from the inside the payload fairing.
The camera seems to be working very well.
The payload fairing is jettisoned.
Okay, the
雷
fairings.
达跟踪正常，遥测信号正常，文昌飞行正常。
The fairings are at the very top of the rocket. They protect the spacecraft, basically.
Yes, once it's out of outer space, once it's out of the atmosphere. It doesn't create any frictions. So we have to lose weight as well as the boosters.
Absolutely.
We drop all of them to increase the propulsion ratio so that we can have better propulsion for speed and for
Absolutely.
altitude.
So are we now out of the Earth's atmosphere?
Yes, we are out of. I think it's more than 100 kilometers above Earth.
The atmosphere is about 70 kilometers.
西沙
Yes,
224
about
跟踪正
70 to
常。
110. Yes.
Okay.
From the voice, we can hear that the telemetry data received from the Xisha Islands, the ground station located on the Xisha Islands, received the data, and it shows that the data
厦
is
门217跟踪正
works
常
properly.
2521遥测信号正常。
So normally there are 2 different kinds of observations. One is telemetry tracking, another is optical observations. So once it's above the optical observation capabilities, we'll rely on the TTNC, telemetry tracking control command.
As Mr. Xu mentioned, we have optical telescopes to observe the flying, and also we have ground-based readers to measure the trajectory of the rocket.
And that's what we've been hearing.
西沙3113跟踪正常。
Yeah, just now, as we've been hearing, those are personnel on the ground, some in Shisha Islands, to keep tracking the flight of the rocket.
The voice mentioned the 313 is the trajectory tracking radar we use in every mission from the Wenchang Satellite Launch Center.
Understood. So now this will be actually a longer phase in that flight. You know, we've had the boosters come off, we've had the fairings come off, we've had.
But this is still the critical moment because the core engine has experienced a couple of times of failure in the past 4 missions. So we have to make sure that we witness the separation of the first stage with the second stage, and the core engine burns properly so that we can ensure the
224跟踪
success.
正常。
The first stage used, as Mr. Xu mentioned, the cryogenic propulsion system with liquid oxygen as the fuel and the liquid hydrogen as the fuel and liquid oxygen as the oxidizer. It has a very high specific impulse, so this with little consumption of fuels, it can provide much more.
Now the first stage
energy.
and the second stage.
Great.
Rockets are being separated. We're hearing applause from the control and command center. Everything seems to be working just fine.
So the second stage we use the YF-75D rocket engines, which also use the liquid hydrogen and the liquid oxygen as a propellant. The thrust is smaller, but the specific impulse is even higher than the first stage.
And later in the flight, that engine on the second stage rocket will be shot for a while when the rocket is cruising.
Yeah.
And there will be a second ignition later in the flight.
Exactly.
Is that correct?
So you can see from the 3D animation, we have data links from the ocean surface to the I believe that is a ground space tracking ship and to the vehicle. And also, as you mentioned, after this spacecraft, the rocket enters what we call so-called the parking orbit. The rocket engine will be shut down, and we will have a coasting phase. with no propulsions, and we will have the second ignition near the equator to have the lunar orbit from the low Earth orbit to the lunar transfer orbit. Now we can see the videos mounted from the camera mounted on the rocket, and also this is the camera mounted near the rocket engine. We can monitor the working of the YF-75D.
You can see the flame coming down from the underpart, which is the burning of the engine.
And it says second stage engine right there on the upper right corner of your screen, indicating what this camera is showing us. And these cameras do seem to work extremely well in outer space.
And you see that because videos always have a very large amount of data, so the transfer rate from the spacecraft, from the rocket to the ground station, has a very high data transfer rate. So this is a very high requirement.
And how long is this process, until the engine shuts off for that brief period until it hits a second ignition?
It normally takes a few minutes.
A few minutes.
Yes. So it very much depends on the orbit that you are planning. So this is a translunar orbit. So it depends on different missions. So the timings are different.
So we're basically waiting for when the rocket and the spacecraft eventually hits that translunar orbit.
Yeah. We will have number of maneuvers before it takes off to the lunar orbit, translunar orbit. And then during that course, we will have a number of corrections. It depends on the precision of the insertion of the spacecraft to that orbit.
What type of maneuvers?
It's like Professor Yang mentioned that once we're leaving the Earth orbit, we'll accelerate to the lunar orbit. And once we reach the lunar vicinities, we have to slow down, what we call a brake, to insert into lunar orbit. So that, and also we will descend gradually from a higher altitude, like 300 or 400 kilometers, to eventually less than 100 kilometers, so that we can prepare for the descent of the ascender and the sample return mission.
Well, you see from the camera mounted on the rocket, we can see that the rocket itself is already under the sunshine. Although we in Beijing here is still at night.
二级依次关机。
Great. The first shutdown of the rocket engine on the second stage. So now we are in the coasting phase.
The coasting phase.
Yeah. So it's already in low Earth orbit with altitude of about near 200 kilometers. We will fly to, as I mentioned, fly to a place near the equator and then ignite again.
Help us understand a little bit more about this process. When the engine has shut down and the rocket is coasting, what's happening now in this process?
So first we need to know that because we choose this kind of procedure because of the location of our launch site. Because we don't have a launch site at the equator or near the equator, so we need this coasting phase to adjust its orbit. So the orbit is determined by the points where the engine is shutting down. So we need to have an orbit with the apogee near the equator. So we only have this choice to have a coasting phase and then ignite again, and finally it can enter in orbit with the apogee near the equator. So that's the necessity of this kind of to enter the Earth-Moon transfer orbit.
Mr. Xu, at what point do we know we can reignite again? What are we waiting to see happen?
Well, probably you can see from the telemetry and tracking control ship that they will. It is near the equator. As you mentioned, the launch site is also near the equator. So we're adjusting the spacecraft to the equator, the Earth equator, so it can reach at the apogee point, as Professor Yang mentioned, and then we fire to adjust so that it will be in the flat face of the equator, and then increase the speed so that it can goes to the perigee where it can have a longer and more higher velocity compared to the current one. So as we call it, sling off by the Earth's gravity to the lunar orbit.
Usually, we also call this second burn of the engines a perigee kick. A perigee kick can be achieved by the second burn of the end stage, and can also be done by a separate rocket engine. Usually, for instance, during the years before, when the space shuttle launched a deep space probe, usually it uses this kind of perigee kick engine. It will be a very small, solid rocket motor. Well, because we know that for the Long March 5 series and of Long March 3A series, we have the capability of the second ignition. So we don't need this kind of separate motors. We only need the engines to shut down first and then ignite again.
So as we call it, to escape from the Earth gravity, the Earth orbiting satellites have a lower velocity, where compared to this mission, you go to the moon, you have to escape the Earth gravity. So we need to fire multiple times in apogee and perigee, and to sling off the spacecraft to the lunar orbit.
During this coasting phase, although the YF-75D engine is not working, but we still need to control the attitude of the spacecraft because we need the correct orientation of the antennas to send the data to the ground and also to prepare for the second ignition.
How do we do that? How do we maintain?
We use some other thrusters, some kind of small thrusters, because you know that at this altitude there will be no atmosphere, so we cannot use other measures. We can only use the rocket thrusters, but much smaller than the, as I mentioned, the main engines. So we use these thrusters to keep the attitude of the spacecraft and also the orientation of the antennas. But still, now we have the link from the rocket to the Tianlian data relay satellite.
This is a rather long process that will likely take a few more minutes until we see that second ignition again.
You see, now we can only see the 3D animation. This is because, as I mentioned, the videos, transferring the videos need to transfer a large amount of data. So only a ground station can do that usually. For a rocket, usually we don't have this high gain antenna to transfer videos. So you see in some phases there is only critical data transferred, so there is no video.
We're also looking at the flight time to the left of your screen. 1,038 seconds into the flight now.
So the second ignition is approaching.
The second ignition is approaching. This is what we call a coasting phase. It takes a few more minutes until we can see that second ignition happen.
So the second ignition is also a very critical step for this launch, and only a few countries can do this. If your end stage have the capability of the second burning, you can do a lot of work, such as the launching object into a high elliptical orbit, which is very useful in deep space missions.
You know, let's leave it for now, because this will take another few minutes until we see that second ignition happen. I want to continue to talk to you about what will happen on the moon. When will we see the deployment of the lander on the moon?
Well, as Mr. Xu has mentioned, we have some instruments on board the lander, because you see, we need to choose the samples, and the samples must be collected properly. So we have a lunar penetrating radar, which will measure the structure under the ground, and we can choose the right place, because you see, we not only need to have a drill deep under the ground, 2 meters, and also we need to know other references of this. But we must have done this within 14 days, because as we have discussed, the design of this spacecraft can only work in in the daytime of the moon and cannot work or cannot survive during the lunar night, which have very extremely cold environment. So we must do this with limited time, and also the scope we also must be designed very carefully. You have asked the question about it is automated or controlled by the ground. So we do have the data link between the ground and the lander, but you see that because the distance between the Earth and the Moon is about 380,000 kilometers, so there is a time delay. So for any actions on the lunar surface, we must consider this influence, and also the operations of the robotic arm, the scoop, and also the drilling. We must consider this, and also another challenge is the packing of these samples. We have the rocket cores and 2 meters under the surface, and also have the reckless. We also need to consider the influence of the flames of the rocket engines of the lander, because this also will have influence to the samples.
Will we be able to see that process as it happens?
Well, I think there are a number of cameras that has been mounted on the spacecraft and the descender. I'm sure we will see some of the images. The collecting process might not be easily visible, but the descending and the ascending process we will see quite clearly, as we experienced that from the Long March 3 and 4. The Chang'e 3 and 4 missions, which has descended to the lunar surface and the rovers itself. So we do have cameras that is working very well, but as Professor Yang mentioned, the cameras and the images take a lot of bandwidth, take a lot of capacities of the telemetry and tracking system. So from the lunar surface to the ground will take some time to process, but I'm sure we will see some of the images.
The tasks ahead on the Moon, including the drilling, the sampling, the collecting, do we know how time is planned? Do we plan everything down to the last detail, or do we allocate this period of time for each task?
Well, this depends on the plans by the team itself. You see that there are multiple choices, and also after landing, as I mentioned, there are also many other important and critical tasks. We need to measure the accurate coordinates of the lander to prepare for the ascending procedure, and also
so this can be pre-planned in advance.
Exactly.
Everything will have to be.
So we have many multiple steps, and also as Mr. Xu mentioned, we have some instruments such as a panoramic camera. With this camera, we can see the images from the lunar surface and check the situation of the lander itself and choose where to get the samples. So this kind of operations can be designed after the landing procedure and then determined by the commander on the ground control.
Let's talk about, as you mentioned, samples. Let's talk about why we need these samples. By studying these samples, scientists say that we can better understand the volcanic activities on the Moon and the age of the Moon, maybe. So, Mr. Xu, how are we going to work with those samples that we make painstaking efforts to collect?
Well, these samples, first of all, have with the COVID-19, the word quarantine, but in our space sector, we also have what we call interplanetary quarantine. So this sample has to be properly sealed to make sure that it doesn't have interplanetary infections, like with what we call aliens, maybe some other germs,
like what you see in movies.
Yes.
Like you can.
So these has to be very carefully handled, especially sample return missions. Secondly, is that the samples, once returned to the Moon, to the Earth, we will have scientific communities to study very carefully. This will be beneficiary in number of areas, including chemical areas, including mineralogical, petrological, isotopic, and geological. So there are many domains that we can study the samples and tell a lot of stories from the lunar surface, and in connection to the development of Earth and in the universe as well.
When the samples are brought back to Earth, will it only be China studying them? Could it be shared with other countries?
Obviously, it will be shared by other countries. There are examples before. You see that during the end of 1970s, the U.S. gave 1 gram of the lunar soils as gift to our country. So we have some. We studied these kind of samples and have some articles published on very important, very influential scientific journals. And also, there are examples that the former Soviet Union and the United States exchanged their samples. You see that although the Apollo program bring back about 81.7 kilograms of samples, but these samples are from 6 different locations of the moon. And the former Soviet Union gets samples from 3 different locations other than the United States. So they exchange their samples and they get more meaningful scientific research results. So this time I believe we will get our samples, and no one has get samples from this we call the Mount Rumker, which is at the northwest edge of the Ocean of Salt, which is the largest
This
lunar
is an
mare.
unexplored region.
Exactly. So, so this region it's relatively young. You see that other samples from Moon have a history of 3 to 4 billion years, while this region is only about a history of 1 billion years. Yeah, 1 to 2 billion years. So I believe these samples will change our view to the Moon, especially to the history and evolution of the Moon. And with this study, we can have a better understanding of all the hypotheses about the formation of the Moon, and also together with the history of the Earth-Moon system.
You know, when it comes to cooperation between countries in terms of its, their respective space exploration programs, some say, this is just about competition. You're going to have an advantage in your space exploration, whether it's lunar or other celestial bodies. How do we understand China's space program? Is China in competition with other countries, namely the United States and Russia, or is China in a better place now to cooperate and collaborate with other countries?
Well, as we have discussed, China is a developing country. We develop our space programs according to our own needs, either an engineering goal or a scientific research goal. So we don't compete with other countries, and it's meaningless for us to compete with other countries. So for this kind of scientific research, they're always top one, because you know that for scientific research, we get to this place, and it is we to get the first to get into this place. But we, as we have discussed, we also will have exchange with other countries to have different to have the samples from different places. So these kind of activities or studies will benefit not only one country, will benefit the whole humankind. So I believe that this kind of operation will be a win-win game for all these space capable nations, and in the future it will be an inevitable trend for these kind of countries to cooperate together. I am a member from the Moon Village Association, and the only founding member of the Moon Village Association with, from China. And our goal is to promote the cooperation between different countries, either between the governments or between the space agencies, industries, or universities.
Mr. Xu, your take on this?
Well, I think, there's a European saying that competition works faster than cooperation.
We're hearing that the second ignition is taking place as we speak. Now 1600 seconds into the flight, almost 1700, the second ignition has happened.
So this second ignition of the rocket will accelerate the spacecraft from the speed of 7.8 kilometers per second to about 11 kilometers per second. So that will be the Earth-Moon transfer orbit, which will be a very high elliptical orbit.
And Mr. Xu, help us understand what we're waiting to see here after the second ignition.
So after the second ignition, we will see this increase, as Professor Yang mentioned, increase in velocity. So with the basically the spacecraft is in the equator, above the equator exactly at the moment. So we will increase the speed so that we can just reach the transfer velocity, so it can go to the lunar orbit at the appropriate, like we call it perigee point.
It will take another few minutes until we know whether we have hit that orbit.
Yes, because the second stage uses the quadratic propulsion system. It works longer. It works longer than the first stage.
Yeah, it's very interesting because a lot of people watch this say that for all these efforts and for all, the challenges that we will encounter in the later stages of this mission, the samples brought back to Earth don't have immediate impact on our world today. All the things we talk about, understanding the moon, understanding how it was formed, understanding the age sort of the moon, and dating all of those volcanoes, they don't have an immediate impact on our lives, on our world now. Professor Yan, how do you say to people who are rather confused or who don't understand why we go through painstaking efforts to do that?
Well, you see, for space activities, there are direct returns and indirect returns. For instance, the navigation satellites, the Earth observation satellites, the communication satellites, which have served our daily life directly, so we can understand that and feel the necessary and the importance of that. But for other scientific research missions, such as the manned space activities and the deep space missions like this Chang'e-5, most of the returns are indirect. So it is our duty, it is we, staff of the employees of the space industry, to give a connection between the public and our space field, to let the public know the importance of our activities and know the returns, the great returns from this space activity. There are examples. Analysis shows that the Apollo program, the manned lunar missions, have a return rate of more than 6 or even 11. That means that $1 invested to the Apollo program, there will be returns to the whole society more than $11. So that is only a very limited analysis. So you see that it is very necessary for us to introduce the importance to the public.
Are we looking for the returns here, multiple times returns here, or are we looking into a future that could benefit all mankind, Mr. Xu?
If you see that the number of satellites that is working above us on the Earth's orbit, we can say that you can tell the difference and the importance of space by switching off the space infrastructure for one day. Then you will see that you can't tell the weather, you can't tell where you are, the navigation shut down, your phone shut down, the communication shut down. So everything will shut down. So from these lunar missions, we'll see that this is a very first step to become for humanity to become an interplanetary species, so that we can go to other celestial bodies, even planets. This is a very first step that we take as a human being to be a spacefaring species.
Let's indulge ourselves here and expand our imagination. With this step, we're endeavoring with the moon. What could the moon do to mankind here on Earth? Because people have talked about energy, right? People have talked about possibly relocating the population to the moon one day. Just help it. When we expand our imagination, what could the moon do?
Well, moon is not the ideal place for immigration. So in the future, it is only an outpost of human being. And on the other hand, the moon have a very plenty of the helium-3. Helium-3 will be a very ideal fuel for the potential fusion power, which can solve the problem of energy supply of human being. It is said that the helium-3 on board the lunar surface, can be used by human being to supply energy for us.
Years.
Yes, for more than thousands of years. So that is a very potential utilization of the lunar resources. And also because, as we have discussed, there are water ice on the lunar surface. So in the future, we can utilize this kind of water, because you know that the moon is much smaller than the Earth. To lift up from the moon is much more simpler than the Earth. So we can use the water to make propellants. So the moon can be a potential outpost for the human being to exploration and exploitation of other celestial bodies of the solar system. So there is one choice. If we want to go to Mars, we can use the moon as our basis and produce propellants and prepare for these kind of missions.
So you can see from this picture is a great picture, seeing that you can see from the Earth from the spacecraft. So it was a great image from the lunar orbiter. So the Chang'e-5 is taking picture of the Earth's surface before it goes to the moon.
Yes, that is a beautiful picture of this blue planet we all call home here. And this is the second stage engine, as it says on the upper right screen.
So this is a camera mounted with a direction to the backwards of the spacecraft. So you can see the background is the blue bubble, the Earth. And
isn't the next development the deployment of the solar? Are we looking to
It will be a separation. Once it's shut down, we'll have separation of the second
It's
stage.
shutting down again. We just heard from.
Yes, we can hear the voice that the second stage is shut down.
It's
So the
shutting
next step
down.
will be the separation of the spacecraft with the end stage of the rocket.
Yes, we're looking forward to seeing that separation
报速修正关机。
of that spacecraft and the rocket, or what's left of the rocket.
The voice also reported the shutdown of the small rocket engines for the correction, a small correction of the orbit to make it more accurate.
What does that indicate? What does that tell us?
Because the YF-75D have a very big thrust, so we need small engines to correct the final orbit to make it more accurate.
So
And
that means it's already in orbit.
It's already in orbit. We're now about 36 minutes into the flight. We understand the spacecraft is already in orbit. We're waiting to hear official announcement about the flight
Well, you can
from
see
Control and Command.
from the image, you can see this spacecraft is very stable in relative to the
地
Earth.
键分离。
So now there's a
The
separation.
separation of the spacecraft and the rocket. This is a crucial step in the flight,
Exactly.
indicating now
so
that
the separation is confirmed by the telemetry data, which can be checked and examined from the ground and also from the camera. We can. This is a video from mounted on the end stage of the rocket, and we can see. You can see the thrusters of the orbiter of the Chang'e-5.
So the spacecraft is now on its own,
It's
which
on
is
orbit.
which is what we intended for.
So
It's now in orbit.
So the next, So the next critical step will be the unfolding of the solar panels of the orbiter. With this step, we will have continuous power supply to the spacecraft.
And we can see the unfolding of the solar panels, right? Do we have cameras that will show us the unfolding of the solar panels?
I suppose so. So we also, as we have discussed, we need the telemetry data to be transferred to the ground. So this is still the engine from the rocket.
So basically, in layman's words, we're fine-tuning the spacecraft as it hits that orbit now. It looks like we still need a couple more minutes until everything is in place and we might hear an official announcement about the status of the flight. Let's talk more about what's going to happen with the main mission this time, the sampling and the returning of those samples.
景山，我是文昌。
What about the challenges of the return capsule? We know that they will return to Earth, they will re-enter the atmosphere at very high velocity, and then it will land in grasslands in Inner Mongolia. I suppose that's what's going to happen. Talk to us about the potential challenges there.
You know that we choose to recover our re-entry capsule in the mainland of China. You know that the difference from the manned missions from the low Earth orbit is that we don't have much choice, and also the window is very, very narrow.
Professor Yang, are those the solar panels we're seeing there?
No,
I can't quite make. So the solar panels have not been.
So we still need the report from the ground staff to report this.
I'm sorry for cutting you off. Please go ahead.
To achieve this goal, we choose what we call the skip re-entry, which means that the spacecraft, the re-entry capsule, will not descending to the ground directly. It will descend from the outer space to about the altitude of about 60 kilometers high, and then raise its trajectory to go back to outer space again, and then going down. To have this kind of measures, we can adjust the landing point in a very wide range. So with this measure, we can land this spacecraft to our mainland of China, or otherwise we will have to recover this spacecraft in oceans. So you see, the United States choose the oceans to recover their Apollo spaceships, but we don't. You see that this needs a very large scale rescue ships, rescue fleet. So we choose this, which can reduce a lot of the cost, but this makes the complexity of the mission itself. You know that the re-entry capsule is a very small one, much smaller than the Shenzhou spaceship. So the tracking of this re-entry capsule is very difficult. You see that tracking so small spacecraft like this Chang'e-5 re-entry capsule with a speed nearly 11 kilometers per second is very, very difficult. We have experienced this during the Long March 5 T1 missions, but that's very successful. And also, this kind of trajectory tracking will be very critical for us to get a very precise prediction of the landing place, and also to have the rescue teams to the place at the first moment.
And Mr. Xu, before I get to you, help us understand what's happening here with this picture.
This
visual.
is what we call the separation of the spacecraft with the rocket itself. So the spacecraft is in a status where it has integrity checking, self-checking, and also sending signals back to Earth and waiting for the command to deploy the solar panel. So we have just heard from the command control center they have received some information from the TT&C ground stations. So they will very soon send a TT&C signal to the spacecraft once everything is validated, and then it will deploy the solar panel and readjust its attitude with the attitude control systems, either small propulsions or gyros. So it will then face a period of time where it will orbit in the equator orbit of the Earth, and then accelerate later on to the translunar orbit.
How long until that acceleration?
It will take a number of circles around the Earth, and then validate everything and make sure that the spacecraft is ready. I think is in 1 or 2. Within 1 day, I think it will send a signal, and then it will go to the translunar orbit.
So basically, information and data as we speak are being sent and validated by ground controlling command. After they do that, they can give instructions to deploy the solar panels.
As you see that this spacecraft is not always above the Chinese territory, so we're using a lot of overseas TT&C networks. The deep space network of ESA has been used for these cooperations, including the cooperation with the European Space